Welcome, everyone. The amount of atmospheric moisture transport into the Arctic is an important climate variable for understanding middle and high latitude interaction and for looking at resulting changes in the Arctic climate and on surface conditions, and in particular, the underlying sea ice cover. Moisture transport can affect the overlying atmospheric moisture content and its associated radiative impacts. It can also directly influence the amount of precipitation falling onto the Arctic Ocean. These processes have implications for model representation and prediction and for reanalyses. So the modeling team has previously looked at atmospheric rivers in August 2022, and the IARPIC atmospheres team had a meeting earlier this year on a similar topic to this as well. So here today, we'll take a look at some new investigations on this topic, and in particular, the effects of atmospheric moisture transport on Arctic conditions. So without any further ado, our first speaker is Chen Zhang. She is a postdoctoral associate at the University of Colorado at Boulder. And the title of her talk is The Role of Atmospheric Rivers in the Moisture and Energy Budget of the Arctic. Chen?
Thank you.
And good. We can see your slide.
That's good. Good morning, everybody. Thank you for the opportunity to share our current work on the role of atmospheric rivers in the moisture and energy budget of the Arctic. So as mentioned, atmospheric rivers are long, narrow filaments of enhanced water vapor transport in the low troposphere that is typically associated with low-level jet and extratropical cyclone. A recent work has found that atmospheric rivers influence Arctic climate by enhancing atmospheric heat and moisture transport, increasing cloud cover, which in turn impacts the surface energy budget, potentially contributing to Arctic warming and sea ice decline. And the critical task to study ARs is to develop AR detection algorithm. There have been multitude AR detection and tracking methods as listed in the Atmospheric River Tracking Method Intercomparison Project, also called RMIP. So RMIP is an international collaborative effort to understand and quantify the uncertainty of AR research based on the AR detection algorithm below. So far, there have been 36 AR detection methods, and many of them have been primarily developed for mid-latitudes, although some have been adjusted for use in polar regions. Particularly, uncertainty from different AR detection methods exceed that of model and reanalysis differences. Therefore, the differences in AR-related moisture and energy budget of the Arctic across a variety of AR indices still need to be quantified. So there are three specific scientific questions that we aim to answer. The first one, to what extent do ARs contribute to atmospheric heat and moisture transport in the Arctic? And how does this vary spatially? And the second question, what are the impacts of ARs on surface downward long-wave radiation? And what's their climatological contribution to Arctic downward long-wave radiation? The third question, how do the above process vary across different AR indices? And to deal with these questions, we mainly focus on ERE5 reanalysis data. And we sample the data at 3-hourly intervals from January 2000 to December 2019. We focus on this recent 20 years to incorporate as many AR indices from the RMIP catalogs, making it easier to compare them based on the same time period. And we calculated integrated moisture static energy transport, MSE, and integrated water vapor transport, IVT, from ERE5 reanalysis to evaluate AR-related atmospheric heat and moisture transport. And we also evaluate AR-related surface downward long-wave radiation impacts using ERE5. And we applied 11 AR detection algorithms that cover the Arctic region, with 6 of them retrieved from the RMIP Tier 2 catalogs. So these 11 AR detection algorithms are grouped into 3 categories based on their climate criteria and their application in polar or global regions. So the first category we call polar ARDTs, including the specific 6 AR detection algorithm or ARDTs. So the first one is Purdue 85th percentile climate threshold with IVT-based algorithm. This is article-specific, using 85th percentile climate threshold on the IVT measurements without any additional absolute threshold. And last 3 ARDTs are global with a polar constraint or polar adjusted AR detection algorithm, meaning that they apply an additional absolute threshold of 100 or 150 kilogram per meter per second. In combining with the similar 85th percentile climate threshold. So initially, this polar constraint AR indices in the polar regions designed to capture the extreme precipitation associated with AR. And the last 2 ARDTs are widely VIVT or widely IWV ARDTs, and they are polar extremes, meaning that they apply a more restrictive 98th percentile climate threshold with either polar IVT or the integrated water vapor IWV measurement. So overall, the first category of polar ARDTs have been widely used in the polar regions for the AR research. And the second category are global ARDTs, including these 4 specific ARDTs. These are also IVT-based algorithms, but with relative or absolute thresholds at least 250 values. And these global ARDTs are initially designed for mid-latitude, but extended to cover the polar regions. And the third one, deep learning-based ARDT, no threshold use, but trained on 500 experts, potentially to capture the strong AR events in lower mid-latitude. So in the following slides, I will use the blue shades to visualize the results of the polar ARDTs, and the red shades to represent global ARDTs with the purple color for the deep learning ARDT. And the color gradient from dark blue to dark red indicates an increase in the climate threshold. And so the first result is the zonal mean AR occurrence frequency as a function of latitude during each season across the entire 20 years. So we see that there is a large variability of AR occurrence frequency, and the climate criteria has a first order influence on the AR occurrence frequency, increasing the climate criteria from the polar ARDT, the blue colors, to the global ARDT in red, and the polar extremes ARDT in cyan colors. The detected AR occurrence frequency decreased dramatically. Specifically, the polar ARDTs using the 85th percentile climate threshold correspond to the largest AR occurrence frequency. However, we also noticed that applying the additional absolute thresholds, like the polar adjusted ARDTs, result in lower AR occurrence frequency, and they're compared to the Purdue ARDT in dark blue without using any absolute thresholds. And their differences are largest in spring and winter, but to a lesser extent in fall. Other ARDTs detect much lower AR occurrence frequency, even lower than 2%. And most ARDTs shows ARs decrease dramatically with latitude. So here we want to point out the Purdue ARDT and the Wiley ARDTs exhibit only little seasonality. And next figures are the longitudinal distribution of AR occurrence frequency at 70 degrees north, so this latitude, during each season based on the 11 AR detection algorithms. So, and also the gray and the black color at the base of each figure denote where the land and the ocean are at this degree. So we also see that the Purdue one are in dark blue, and the Wiley ARDTs in cyan colors show little longitudinal distribution and seasonalities that is due to their personnel-based AR detection algorithm. And we found that the highest AR occurrence frequency in the Atlantic sectors in the cold seasons, winter, spring, and fall, but the lowest AR occurrence frequency in the Atlantic is observed over Greenland in summer, with the exception of the Purdue ARDT. And next, we evaluate AR-related atmospheric heat transport. So this figure shows the latitude, the zonal mean AR contribution to polar MIC transport during each season based on the 11 AR indices. We still see there is a large range of AR-related MIC transport across different ARDTs due to the wide range of AR occurrence frequency that we saw before. And the polar ARDTs using the 85th percentile climate threshold, the blue colors, generally correspond to the most polar MIC transport. And overall, AR account for polar MIC transport ranging from like greater than 25% to even less than 2%. And most ARDTs shows that AR's contribution to polar MIC transport decrease with latitude. And this figure visualizes the longitudinal distribution of the AR contribution to MIC transport at 70 degrees during the season using each AR index. And still, Atlantic sector received the highest AR contribution in winter, consistent with the largest AR occurrence frequency. And the lowest AR occurrence frequency resulted in the lowest AR contribution to polar MIC transport is observed over Greenland in summer, except for the Purdue one. And focusing on the magnitude, we see that at 70 degrees north, AR contribute to polar MIC transport at a rate more than twice than their AR occurrence frequency for most ARDTs. And the polar specific ARDTs, and like using the 85th percentile climate threshold, agree on the AR contribution mostly in summer, except for the Greenland and the Atlantic sector in the cold seasons. And next, we evaluate AR-related atmospheric moisture transport, similar to the previous figures, but for the results of AR contribution to polar moisture transport. And we see that there is a large range of AR's contribution to polar moisture transport across different ARDTs, and that is due to the wide range of AR occurrence frequency that we saw before. And still, the polar ARDTs using the 85th percentile climate threshold, the blue colors, generally correspond to the most moisture transport, like greater than 40%. And to focus on the magnitude, we see that ARs could account for a greater portion of polar moisture transport than MIC transport, with the maximum from over 40%. And again, as contribution decrease from lower latitude to higher latitude, consistent with the AR contribution to MIC transport. And this figure visualize the longitudinal distribution of AR contribution to polar moisture transport at 70 degrees for each ARDT. And we see that in addition to the Atlantic sector, Pacific sector also shows a larger AR contribution in the cold seasons. And also Greenland shows a minimal contribution from ARs in summer, except for the Purdue one. Focusing on the magnitude at 70 degrees, we see that the contribution of ARs to polar moisture transport is at a rate more than 3 times than of their AR occurrence frequency for most ARDTs. And the Purdue ARDT in dark blue and the polar adjusted ARDTs using the absolute threshold agree on AR occurrence frequency in summer, except for the Greenland. And in cold season, they agree over the ocean, but differ over land. And still, the deep learning ARDT and temperature ARDT are associated with the lowest contribution to the polar moisture transport. Lastly, we assess AR's impact on surface downward long-wave radiation. So the first results are the AR's average AR-related LWD anomalies. So the result shows that AR induced large LWD anomalies, with the largest in winter and increase with latitude, ranging from 50 to 100 watt per square meter, followed by the spring. And smaller of anomalies are in summer and decrease with latitude. And we see that the global ARDT, you identifying the lowest AR curse frequency in the red colors, show larger AR-related surface downward long-wave radiation anomalies as they capture the extreme moisture events. However, when we consider their AR curse frequency across the entire 20 years, the contribution of the surface downward long-wave radiation during the AR events only account a small part of the seasonal total surface downward radiation, ranging from 10 to 15% to less than 1% due to their different ARDT used. And opposite to the magnitude of anomaly, so the polar ARDTs using the 85th percentile climate threshold with higher AR curse frequency corresponds to the most overall LWB impact. However, the global ARDT that's having the largest anomalies display the smaller contribution to the climatological surface downward long radiation. And also most ARDT shows the AR's contribution is largest in summer and smaller in winter, with the exception of Purdue ARDT. And these findings suggest that identifying the extreme events with large anomalies doesn't indicate a large overall climatological impact. So this is the conclusion. We find that there is a wide range of AR current frequency from 1% to 12%, depending on different ARDTs. And the large AR current frequency results in large range of forward moisture transport and the heat transport, as well as the surface. So that's all I want to share today. I would like to take any questions. Thank you.
Thanks very much, Chen. If you have a question, you can raise your hand. That's under the React button these days in Zoom, or you can unmute and try to get our attention. I just see that Wilbert has, oh no, I believe that was applause, sorry. Chen, just for clarification here, so you looked at many detection methods. They are mainly characterizing the instantaneous water vapor transport. Are any of these techniques associated with the duration of the transport? For example, a large transport over a few days, is that a threshold that is necessary in any of these methods?
Oh, sorry. So do you mean that whether any ARDTs using any temporal thresholds like?
Yes.
And as long as so here, and yes, like Purdue one that I developed before during my PhD, that I used 24 temporal criteria, like is 1 day. Also, the M23 was developed by PNNL, also used temporal thresholds. So
Okay.
So mainly these two use the temporal threshold.
Okay. And so just as an understanding of the transport results that you found, you showed the spatial distributions of the atmospheric rivers by longitude. are those strongly dependent then on the distribution of the total moisture transport? How would the total moisture transport differ as opposed to just the atmospheric rivers?
Yeah, so this is the distribution of air current frequency. So actually, this pattern is consistent, like except for the Purdue ARDT and the Wiley one, because they are based on the percentile AR detection algorithm. So other ones using the absolute thresholds, the detected AR results are consistent with the climatological IVT or IWV. Like for example, according to the CC equation, like moistures are much stronger in summer, but lower in winter, like in the Arctic. So the resultant ARs are more frequent in summer and the lowest in winter. Similarly, is for the zonal longitudinal distribution. We see that the maximum air occurrence frequency were over the Atlantic Ocean, which is the location of the storm, the end of the storm track over the Atlantic Ocean. And also Greenland, we also see there is a minimal air current frequency because that is the Greenland is very dry and cold all the year around, particularly in summer. So actually, except for the percentile-based ARDTs, other ARDTs, the results mostly correspond to the climatological distribution of IVT or IWV in the Arctic.
Okay, very good. Are there any other questions for Chen? I'm looking, I don't see any. Oh, Wilbert has his hand up. Wilbert.
Yeah, I mean, there's obviously some objectivity in identifying atmospheric rivers, but there's also, on the other end, there might be some structures that all algorithms kind of should agree on, right? And the difference that you're finding in the different algorithms is maybe a little bit concerning in that respect. I'm wondering, I mean, probably each of these algorithms have a different kind of maybe a tuning parameter or so, maybe a threshold that can be adjusted that has some subjectivity to it. Is there a way in which the range of these algorithms can be reduced a little bit so that they kind of more or less converge on identifying the same set of events?
Sorry, like you mean, I want to clarify, like you mean whether these all different bunch of AR indices can be reduced to some specific categories that for use in particular question? Is that what you mean?
Sorry, I didn't quite get that, but I was wondering if there is a way to fine-tune some of these algorithms, especially the ones that are extreme, that have either no or the maximum of the number of detections, basically. Is there a way to kind of fine-tune some parameters in these algorithms so that they kind of converge to more or less the same number of the same frequency of occurrence?
So whether, sorry, so you mean whether all these AI indices can convert to the same number of AI result if they
Right.
tune on some parameter, right?
Yes.
I think, and the IMAX threshold is the first order that influence the results of the different AI current frequency. And if we like increase all the criteria of climate threat for all these AI indices, like to the, for example, 98 or at least 250, this very strict criteria. So the resultant AI current frequency will be mostly consistent. But for polar regions, the criteria should not be the same as for the criteria in the mid latitude, because so in most of AI indices have been developed for mid-latitude that because they want to capture the strong precipitation in the mid-latitude. However, in the Arctic, ARs are also important in terms of surface radiation. And if we consider the AR's impact on surface radiation, we should not use the same criteria as mid-latitude because the criteria in mid-latitude to capture the precipitation is much stronger than the consideration of the surface radiation impacts in the Arctic. So basically, my main point is the global ARTTs should be used cautiously when studying the atmospheric rivers in the Arctic because they only extract very extreme AR events. And the other polar ARDTs can be used for different purposes in the Arctic region. So that's the main point.
Right. So maybe don't use the global ones, but maybe another way of phrasing my question is suppose that you as an expert on this would identify a bunch of events in the historical record that you would definitely classify as atmospheric rivers. Could you fine-tune each of these the high latitude specific algorithms that they all agree that these are atmospheric rivers, basically? Is there some freedom there?
Yes, I think the freedom is the climate criteria, or also whether use the absolute thresholds. So whether we should use the absolute threshold to constrain the AR detection in polar regions or not. So that's the factor that it may influence the results differently.
Okay, right. Great, thanks. Great talk.
Did you happen to look at or do you plan to look at the impact of the shortwave down welling forcing?
Oh, so for this work, we didn't look at the shortwave down for all the indices that previously we only used the shortwave down using the first one, the Purdue 85 IVT.
Okay.
With absolute thresholds. So that is not covered in this work. This was in the previous work.
Okay, thanks very much. Okay, let's go on then to our next speaker. And our next speaker is Rudra Thacker. He is a graduate student from the University of Wisconsin Madison. He works with, his advisor is Elizabeth Maroon. And the title of his talk today is The Influence of Climate Change on Arctic Atmospheric Rivers and the Impacts on Sea Ice.
So I'm trying to share my screen. I guess I'll just share my desktop if that's easier. Does it still work?
Yes, we can see your desktop.
Awesome. And the presentation hopefully as well.
It's moving in slowly and there it goes. That's good.
Awesome. Hi, everyone. Thank you for being here. My name is Rudra Thacker. I'm a graduate student at University of Wisconsin Madison. I see some familiar names in the participants. So for some of you, it might be a revision of what I've been working on. But it's basically, does the definition of Arctic atmospheric rivers matter in changing climate? So Chen did a fantastic job in explaining how these different algorithms captures different atmospheric river dynamics. And where I am tackling this question is from another perspective, that what happens if even using one algorithm, how large could be the uncertainties when you factor in climate change using climate models. So that's the overview of the talk. I would like to thank my collaborators, Steve Webris, Christine Shields, Alice Duvivier, Marika Holland, Laura Landrum, Michelle McLennan, and Leonard Bartholomew. And let's go in. Yep. So I don't think I need to reiterate what atmospheric rivers are, or ARs, but just to say again what Chen just said, there are long, narrow corridors of moisture and warm air. They are very efficient transports, like very efficient mechanism of transporting moisture from lower latitudes to higher latitudes. And according to a study in 1998, they could account for 90% of the poleward moisture transport. So a lot of moisture, a lot of heat, a lot of precipitation, and therefore Arctic being so dry, these events could have large impacts on Arctic system. So what do we know so far? There have been studies by Wang et al. And Zhang et al., which shows that summer and winter Arctic ARs tend to cause a net sea ice loss. This is studied in present climate. So even in present climate, they have a negative impact on sea ice. And these are through numerous mechanisms, pushing of ice due to winds, changes in downwelling long-wave radiation, short-wave radiation, snow on ice, rain on ice, etc. But there is a large net sea ice loss. The other studies, Ma et al. 2021 and then Colby et al. 2023 show that Arctic ARs are changing as the climate changes. So as the climate warms up and there's more moisture available in the atmosphere, they're becoming more frequent and more intense. More frequent meaning that they're getting the number of occurrences are increasing in the Arctic, and so is the duration of an atmospheric river. And more intense means because they have more moisture, they are transporting more moistutic energy or energy in general towards the Arctic. So what is this talk going to be about? Again, while we explored a lot of different stuff, I'm just going to give a broad overview, focusing on the title, How Definition Affects These Results. And so the questions we would be asking is that, what are future AR changes when you look at a transient climate change climate model under continuous CO2 forcing? What are the seasonality of these AR changes in the future, impacts on sea ice, and how all these results change based on how you're defining your ARs. So there's two schools of thoughts. One could be definition of ARs based on present climate, and the other one is definition of ARs based on future climate. And we'll get to these questions in a bit. So data and method, for this study, we use a climate model called Community Earth System Model 2, or CESM2. It uses 40 ensemble members. The historical run in the model goes from 1850 to 2015, but what we use is a historical simulation from 1980 to 2014. Also, we call it as a present climate situation. And then the future simulation runs from 2015 to 2100 under the SSP 370 scenario. The data is 6-hourly, so we can track those extreme events, and it's on a 1-by-1 nominal grid resolution. So method, as Chen again mentioned, the method we use is Jonathan Willie's algorithm, mentioned in 2019 and 2021 papers by him. And it's a very simple method. It's a polar atmospheric river detection method. So it has been catered for polar detection, and it has a couple of limitations. I'll get to those in a minute. But the process is like you just take the 6-hourly data of vertically integrated meridional vapor transport, which is just the meridional vapor transport V into Q. And then you look at the 98th percentile, which is sort of an extreme. So the ARs getting detected as shown in the animation on the right would be more of an extreme atmospheric rivers in the Arctic. And there is an additional length parameter of 2,000 kilometers to detect this AR, so they're long and narrow and not too broad. So moving on, in CSM2, once we use all 40 ensemble members, this figure is showing how the frequency looks like in the present climate scenario, 1980 to 2015. And I have shifted the seasons by month. So it's October, November, December as winter, and then January, February, March, April, May, June, and then July, August, September, just because the heat maps were more coherent when you group them through the seasons. So they're representative of what's going on in those months. A couple of things to note here. One is how low the frequency is in this individual season. So on an average, there is close to like 0.6 to 1 AR days in any season. Another striking difference is how defined a seasonality could be. Well, it's not a big difference, but winter clearly has more ARs as compared to summer because of the Barkling instability being stronger in the winter. And we have those obvious hotspots in the winter season, Greenland, the Atlantic storm track sector, the Pacific, the North Pacific region, and some coming over from the Europe and Russia continent, which might be just melting of permafrost in the model simulations. So overall, this fits also well. Like we compared this with RFI dataset for bias checking, and CSM2 is able to perform well as compared to RFI. So that was just a sanity check for us as well. And moving on to how these atmospheric rivers change with future climate, one question I would like to ask the audience here is that hypothetically, if 40 degrees Celsius is an extreme heat wave event in present climate at a given location, is it still an extreme event in the future climate, given that 40 degrees Celsius might be an average temperature for this location at that time, or they're just more frequently observed because the climate warmed up? And I'll wait for 5 seconds if anyone wants to say whether 40 degrees Celsius is still an extreme event or not, or else I'll move on. I'll ask the same question in the end again. So moving on, the way we try to answer this question is using two different methods. The first one is the Hist-Thresh method. So this follows the ideology of defining extreme as how it is in the present climate. So 40 degrees Celsius event, if it's an extreme event right now, it stays as an extreme in the future climate, no matter what year you look at. The other method we use is called IWV scaled method. IWV stands for integrated water vapor or total moisture in the column atmosphere. And this accounts for the background increase in moisture as the climate warms up. So to give you an example how the method works, we are looking at one random location in CSM2 and a time series of the IWV ratio, which is nothing but how monthly IWV changes from 2015 to 2100, depending as compared to 1980 to 2015 climatological IWV. And as you can see, like goes from ratio 1 to 1.6. That means that the background moisture is getting increased by that many times. And then for the IWV scaled thresholds of detecting ARs, you just multiply that ratio with the present climate thresholds of 90th percentile, and that accounts for the increasing moisture. Another way to look at it is this schematic. So the blue line here shows how the moisture changes with changing climate. It's a very idealized situation, so this is not how the moisture would be changing. But the solid gray line shows the historical threshold for 1980 to 2015, and then the dashed line shows that we keep the same threshold in the future climate, whereas the orange line is what our IWV scaled method would be doing, that it's trying to account for that increasing moisture and scaling the thresholds based on that. We move on to some results. So the first one here is showing the Arctic AR frequency changes from the last 35 years of the simulation, 2065 to 2100, as compared to the present climate as defined as 1980 to 2015 time period. And this is the Hist-Thresh method, so defining ARs based on the present climate, no accounting for moisture increases. And what we see here is a remarkable increase of 400% in AR frequency by the end of the century. And that is a lot of change. A couple of things to note here is that this is largely because of how the thermodynamics of the system is changing. So just increasing moisture, following Clausius-Clapeyron relation, and the statistically defined extreme event just getting detected more and more as the climate warms up. One thing that catches my eye here is that the AR frequency does not increase by a lot over the Greenland region. And we haven't checked what that would be correlating with, and it correlates well with how the SST gradient, so sea surface temperature gradients, are changing, and how the NAO patterns are changing as the climate warms up. So that could be just a response of a cooling down in the North Atlantic sea surface temperatures and how that affects blocking patterns across the Arctic. Other thing is that the months of April, May, June, and July, August, September has a widespread increase in the internal Arctic, and that's where the sea ice is. So what this method of detection of AR does is that it captures a lot of melting of sea ice that opens up ocean and more evaporation into the atmosphere. And because from 1980 to 2015, there was no such large amount of moisture present, it just exceeds that threshold, and suddenly everything in the Arctic is an atmospheric river. Moving on to the second method. The second method, the IWV scaled method, scales for moisture And what we see and what I think about this is more of a realistic scenario of what the dynamics are doing to atmospheric rivers. And when I say dynamics, I'm still using it kind of on a loose terms. It could be a number of things. But what we see here is that now Greenland region has a decreasing frequency of AR as climate warms up, again, depending on how your NAO patterns and moisture is changing on Greenland. But there is an increase over land. So Europe and Russia is seeing increase, and over the Canadian archipelago, there's an increasing atmospheric rivers. And in the months of April and June, the Atlantic storm sector kind of becomes more active. And that's where majority of the ARs go in. This is very interesting in terms of sea ice as well, because April, May, and June is when in CSM2, the sea ice is still present and kind of sort of reaching its maxima, even though it's a thin sea ice. And that means there would be a lot more sea ice changes happening during the months of April, May, and June. July, August, September, the summer where there is no sea ice, it seems that the AR genesis and termination is moving more poleward. So it's a widespread decrease across most of the Northern Hemisphere for ARs, other than limited to the Central Arctic region, where we see an increase in percentage. Let's see if this could be because of dynamics or not. And so for that, what we are showing here is wind changes at 700 millibar pressure as colors. So the color red is decreasing wind speed, and color greens to blue are increasing wind speed. And the contour lines here just show the same frequency plots as previous for the IWB scaled method. The solid line here shows increasing frequency, similar to the previous plots, and the dashed lines show negative frequency, and they correlate quite well how this changes in IWB scale atmospheric rivers coincide with wind changes. And we have checked this with sea level pressure, geopotential heights, and they all coincide well. And that means that it's largely driven by how the jet stream changes. So it also has, in corroboration with other studies which show that how the jet streams will change in the future, and they affect the storm track regions and atmospheric rivers. The last thing I'm going to show is how the sea ice evolves during these events in the future climate. And what I'm showing here is the total AR-induced sea ice changes. And we're just going to focus on the months of January, February, March, and then April, May, June. So the red line here shows the IWB scaled method, and the black line shows the His-Thresh method. The solid lines are the ensemble mean, and the shading shows the ensemble spread using the 40 ensemble members. And what we see here is that by the end of the century, the His-Thresh method captures nearly 5 times of sea ice loss as compared to the IWB scale method. And this is coming from a detection and attribution perspective, like how much sea ice loss could be attributed to atmospheric rivers. Well, it depends, first of all, what algorithm you're using, such as Willy or the Purdue 85th percentile quantizer. But for the future climate, it also depends on how you're defining your extreme. So this is another layer of uncertainty that could be there because of these definitions. Another thing I would like to note here is that these are the absolute values of sea ice changes. So the relative values would be much more larger if you're looking at how much percentage of sea ice is lost, given that post-2065, there is much less sea ice to start with. So the relative contribution would be much larger for both the methods. Spatially, if we look at the years 2065 to 2100 and see what are the regions of this potential losses of sea ice, they generally quite follow well how the marginal sea ice is changing in the Arctic, with the exception that the His-Thresh method at this point is capturing maybe random sea ice changes happening in the Arctic, just because the threshold is exceeded so quite frequently, even without a presence of a synoptic scale system in the Arctic. Whereas the IWB scale has a much more modest sea ice changes. And you can see that there are regions where you can see sea ice gain happening, shown in the blue colors. And those could be because of thermodynamic changes like snow, or cooling because the clouds block the shortwave radiation. And we have investigated into that, and it seems like more of a dynamic response. So the gain is not an actual gain, but more like the pushing of sea ice against the coastlines, and that's why they usually accumulate where the coastline is. So that's more of a dynamic response of ARs to sea ice. And overall, there should be a net sea ice loss impact. So conclusions and sum up the talk. These are the questions we started with, and we find that the future AR changes and impacts on sea ice do depend on your choice of method for defining ARs, and it has large influences on the results. And again, we are not even looking at different algorithms, just different definition based on subjectivity of an extreme. And future atmospheric river changes do cause a net sea ice loss impact, no matter what metric you use. It has a net loss signal. However, how big the loss could be depends on what method you're using as compared to his thresh method or the IWB scale method, and it could be as large as 5 times the other one. And with that, I'll take any questions, but feel free to reach out to me for other results or other, if you want to discuss more about this. Thanks.
Thanks very much, Rudra. So again, if you have a question, you can raise your hand. And immediately I see a hand raised by Jack. Do you want to ask a question?
Sure. Thank you, Richard. Great talk, Rudra. I have a question that kind of goes to both of the speakers today, and it's a follow-up, I think, to the last question on the first talk. But I think, Rudra, you didn't quite say it, but you made a very strong case that you have to probably can't use historical thresholds going forward. I mean, you didn't say that, but you certainly made a very strong case. But one thing that I don't think the first speaker did, and I think that maybe the questioner was trying to get her to do, is you chose, I mean, she made a case that you should use these polar specific algorithms, definitely, but there were 6 of them, and she did not come anywhere close to saying which ones seemed to be most realistic. I don't know if you thought about others besides Willy, but you chose to use the Willy one, and I was wondering why, or if you tried playing around with others, and of the Arctic ones, the 6, the 5 others, and just for other people thinking about ARs, you know, which of these algorithms seems to be the most robust? And I don't know if you want to take an answer, or both of you in turn could make a stab at that question.
I can start with the answer, and then I'll leave it to Chen, who has spent more time looking at these things as compared to me. But so your first question, why I chose the Willy algorithm, was strictly from a perspective that when I started working on this project, it was one of the foremost algorithm that was developed back in 2021, and other than the Purdue one, which Chen was working on. So we started with that one so that we can compare at some point with the Purdue algorithm. And also it was able to capture some of the interior ARs in the Antarctic region. So if you're looking at ice sheets and how much deeper into the poles these ARs could penetrate, it really was one of the available algorithms to start with. So it was strictly from what is available perspective. Now that there are more ARs available, I am more relying on one of the algorithms developed by Ankur Mahesh, and he accounts for transient eddies and moisturistic energy to detect ARs as compared to VIVT and statistical thresholds. It actually looks at a cyclone and the moisture transport associated with a transient eddy, which is the physical definition of an atmospheric river, that there should be an extratropical cyclone and there's a moisture transfer happening. So I like that physical definition more, which might be actually agreeing with all the other data set as well, but I haven't explored many other algorithms. And then I also see a question from Patrick, but I'll wait to hear Chen's answer first.
Yes. Chen, do you have a comment then on which of the methods might be the best for the Arctic?
Yeah, I think there is a unique option, unique bias AR index for the polar regions. Consider your specific scientific questions if you want to capture the extreme, like precipitation events. The Willy one may be biased because they are designed to capture the strong precipitation events. However, we see that the AR detection algorithm with the more restricted criteria, they tend to detect the strong extreme AR events, strong extreme AR cases. But if we consider there the climatological occurrence frequency and the extreme events tend to capture
the extreme moisture perturbation, but they contribute to very smaller portion of the total climatological impacts, such as surface downward long-lived radiation anomalies. So I think there is not a unique optional AI indices depending on the different scientific questions. So we should decide which AI indices can be used the best. Yeah, thank you.
I guess I can see, an issue here if you take a definition that is essentially associated with a mid-latitude atmospheric river and then apply it to the Arctic. You can see that if an atmospheric river of that magnitude occurs in the Arctic, you get a profound effect. And the question is whether you're actually showing that or if it's appropriate to use that kind of metric, or if you should use an atmospheric river that is a definition that is more appropriate for Arctic conditions, drier Arctic conditions, and then do the evaluation. So I think it's a question that perhaps might require some additional study. Okay, Patrick, do you have your hand raised?
I do. Thanks, Richard. I agree with your last comment. I think that's maybe the outcome of today for me. But I want to push back a bit on what Jack said. Based on what Rudra presented to me, it suggests you need both those two different definitions because they're telling you unique aspects of atmospheric rivers, right? Because there is the component of this poleward moisture transport that is changing the Arctic atmosphere because you have more of it, and you have more of it because the lower latitudes have warmed and it's being pushed there, right? That's the thermodynamic component. But then you do have the dynamic component as well, where with climate change, the AO or however you want to classify the northern hemisphere atmospheric circulation, it's changing. That can also change and displace and your atmospheric rivers. So I think what I took away is that from Rudra's presentation is you kind of need both of those different perspectives, both the historical threshold as well as the moving threshold, to understand those two pieces, because they're two different pieces. Going back to Rudra, your question about whether a 40C anomaly heat threshold is an extreme event in the future, I think the answer is it depends. It depends on the use, right? Because 40C is set there because, well, technically it probably should be a little lower, but those temperature thresholds are all based on human impacts of heat. And so personally, the way humans respond to heat is not changing in the future. So I would say that threshold is fixed because it's relative to a specific human impact. But in the case of atmospheric rivers, like we're talking about, maybe it's not, right? So I think it depends on this case. But having it fixed, like you said, you showed that increased water vapor transport can help accelerate sea ice loss potentially. I have other questions on that, but let me ask you a question since I've been talking this long, which is, in your methodology, have you considered any kind of interactions or two-way feedbacks between the sea ice and the atmospheric rivers? Because I heard you say atmospheric rivers are forcing sea ice loss, but I think there's room there for, as sea ice retreats, that could be influencing the atmospheric rivers themselves.
So that is a very good question, Patrick. And we have tried tackling that question just as a preliminary work, is that looking at how the genesis and determination of ARs are changing as sea ice recedes, hypothesizing that that's because the sea ice is moving and it's opening open ocean waters. And we do see that the ARs move poleward, even though they originated the same locations in the mid-latitudes or tropical, but they start penetrating deeper into the Arctic. And we think that's because of how the sea ice is receding, not the other way around, but because sea ice moves up and opens up ocean, it fills in the ARs. There is, I know Ian Baxter has worked on water tagging experiments with Hansi Singh, and those would be one of the cool experiments to check and see how these moisture sources are changing that could be related to the sea ice. I have not looked into that yet, but there would be a strong feedback.
Yeah, and I think from some of the Cardinelli and Rose papers, to me it's consistent as sea ice melts back, you change the atmospheric stability. A weaker static stability then could allow these rivers to penetrate deeper. And so I think there might be some feedback there, but yeah, I think that's a really interesting aspect to get at here. Thanks. That's all I had.
Thanks, Patrick. So Rudra, I have some questions about how you showed sensitivity with the sea ice cover. So when you showed that, essentially, were you looking, I'm sorry I didn't pay more closer attention to how you described this. Were you looking at times when an atmospheric river was occurring and then looking at the change in the sea ice cover at that time? Or did you have another methodology?
So I'm gonna share my screen again and go to the presentation.
Rudra, actually, is it okay if I jump in for a moment?
Oh, yeah. Go for it.
Okay. Just want to do a quick time check for folks. We are at the top of the hour. I'm happy to keep the meeting room open for a few more minutes for folks that want to stay and discuss a little more. I'm happy to do that. As a reminder, the recording will be available on the IARPA Collaborations page, and you can find it on our YouTube channel as well. And so, yeah, just want to thank folks who have a hard stop for joining today. If you have any announcements for the Modelers Community of Practice, feel free to put those in the chat. Yeah, and we'll stay open for another 5 or 10 minutes as long as there's questions, and you and Chen are available. So thanks so much.
Yeah.
Thanks, Hazel.
Yeah, thanks, Hazel. So, okay, I'm not gonna share my screen again, but to answer your question, what we do is that we do look at the time steps where AR covers a sea ice region, and then we do an instantaneous sea ice change calculation. So how much the sea ice changed over those days. And then we look at, because it's a long time period from 2015 to 2100, and sea ice goes a drastic background change, like the mean state sea ice changes a lot. We look at the long-term daily climatological sea ice change value. So what is the sea ice change value for 5th of October, and then pass a 5-year running mean to account for that background loss. So as an example, the loss I'm showing is that in winter season, if the sea ice is supposed to climatologically grow by 5%, and during an AR, it grew by 2%, then my figures is showing a 3% loss as an apparent loss. So instead of growing 5%, it grew 2% because there was an AR present, and that 5% is calculated through a 5-year running window on each day.
Okay. Okay, so you attempted to account for the background loss.
Yes.
I'm trying to think of another way to do that. I can't right now. There's no way to turn off atmospheric rivers in the climate model. So
that's something that I have talked to Marika Holland and Laura Landrum at NCAR a lot about, like, how about you fix the moisture, like somehow run the model with, or let's say run the model with the historical moisture level, but the sea ice state is one of the future sea ice, but that doesn't constrain the energetics, and doesn't work well. So
I think the model would hate you right away if you tried something like that.
Yeah, and they were also, they said the same thing, like, I don't think that's physically possible. I'm still thinking about that, whether somehow trying to do a nudged simulation, like nudging the winds. So the winds are nudged and somehow the moisture still is evolving. That's something that Ed Blanchard Wrigglesworth has done, and trying to find some insights about winds versus moisture. But it's hard to do with a coupled climate model. Yeah.
Okay.
That's
very
my
good
answer. Sorry. Yeah.
Any other questions or final thoughts? I don't see any. Wilbert, do we have any modeling team announcements?
Not that I remember. Sorry.
Very good. Okay. I'd like to thank everyone for joining us today. I'd like to especially thank our speakers for their presentations. And we'll see you next time. Thank you.
Thank you all.
Thanks, everyone.
Bye-bye.